All right, hi everyone. So we are going to start with Unit 5, and Unit 5 is all about solving systems of equations. Unit 5 is kind of pretty massive. There's 22 pages in our guided notes packet, as you saw. It starts off decent, right? And then we get into the meat of things in terms of motion problems, simple interest, mixture, and then we end it with some miscellaneous problems that seem to be really fun and kind of lighthearted and nice. So it's kind of going to feel like that as we move through Unit 5. I don't want you to feel worried at all because you have all the resources that you need, and I think that you'll like the way in which everything's organized, right? Okay. So we are going to start Unit 5 today, and when we come back from break, we'll continue. But as I mentioned before, when we come back from break, we are going to meet via Zoom and have our classes there just for the rest of Unit 5. All right, let's take a look at the notes. All right, so Unit 5, solving systems of linear equations. Recall from Unit 4 that we have linear equations in different formats, right? So as a reminder, if we wanted to write an example of a linear equation in standard form, that would be something like 2x minus 5y is equal to 8. That's an example of an equation in standard form. You know this is standard form because your variables are together on one side and your constant is on the other. Next, I wanted to provide an example of a linear equation in slope-intercept form, just again, as a reminder. And you guys have been working through the homework in Lumen, so you've seen slope-intercept form a million times. So an example of an equation in slope-intercept form could be something like y is equal to negative 1/3 x plus 2, right? That's a perfect example. Okay, and Alyssa, that sounds horrifying. So here are your two examples. Awesome. Next, we want to consider that when we write the solution to a system of equations, it's actually going to be in ordered pair form. All right, the solution to a system will always be ordered pair. Remember from Unit 4 that it's an ordered pair because it's alphabetical order, x and then y. All right, we have three types of systems of linear equations. The first type is called a consistent system. We know that we have a consistent system when there's exactly one point of intersection, right? That right there, what I just circled, is the point of intersection. It is where the two lines cross each other. So for instance, if I looked at this carefully and I counted each mark here is like 1 unit, so this is 1, 2, 3, 4, 5, this is 1, 2, 3, 4, 5, etc., then this ordered pair, the points of intersection, could possibly be 1.5 comma 2, or excuse me, 0.5 comma 2, my bad. Okay, so a half, right, because it's halfway through the first mark, so it's a half comma 2. That could be the point of intersection for these two lines. So because they cross at exactly one point, well, that makes it consistent. Notice here, one solution, and you'll just say what that solution is. In this case, that ordered pair x, y. You could have a system where the two lines never intersect. The only way you can have something called an inconsistent system is if the two lines are parallel. If your two lines are parallel, we learned from Unit 4 that they'll end up having the same slope. That's how you know for certain whether or not the two lines are parallel. They'll have the same slope, but they'll have different y-intercepts. Notice here, the y-intercept for my first line is about at that point, and if I continued this line down, my y-intercept is approximately right about here. Sorry about that line being so crappy. So my y-intercepts are definitely different, but the slopes are completely the same. So that would be an inconsistent system. The answer to a system where the lines are parallel would be no solution, because they don't cross. They never cross. So you would say that there's no solution. That should make sense. Let's look at the third type of system, and that is called a dependent system. If you have a dependent system, what that means is that the two lines are actually the same. If your two lines are the same and they're one on top of the other, then they intersect at every single point. And if they intersect at every single point, there is an infinite number of solutions. That's what you would write as your answer to a dependent system. Okay? By looking at the equations, you know that it will be an infinite number of solutions if the two lines are the same equation. Now, you're looking at this system, y equals x plus 2, and negative 3x plus 3y equals 6. And you're probably thinking, those aren't the same. Well, let me prove that to you. First off, your first equation is in slope-intercept form, y equals mx plus b. Your second equation is in standard form, ax plus by equals c. They're not the same form. So how about we manipulate this guy and rewrite it in slope-intercept form? To do that, I'm going to add 3x to both sides. That gives me 3y is equal to, and instead of writing 6 plus 3x, I'm going to write the 3x first. So 3x plus 6. Then I'm going to divide every term by 3. That leaves me with y is equal to x plus 2. And what do you know? They're exactly the same. Originally, they looked different, but I manipulated the second one to prove to you that they're identical equations. And if they're exactly the same, well, they're the same line. So there would be an infinite number of solutions. Okay, those are your 3 types of systems. So what that means for all of you guys is that when you're answering or solving these systems of equations, you will either have one solution and you'll write that as an ordered pair, or you'll have no solution, or you'll have infinite number of solutions. So you have those 3 choices when you're solving these systems of equations. So I want you to think about that as you're solving. It's possibly one of those 3. Let's go back to the notes. In addition to there being 3 types of systems of linear equations, we're going to consider the 3 methods for solving systems. There are other methods, like we could use matrix algebra to solve a system, but we're not going to do that in this class. So if we use a technique of graphing, we know that we can graph lines by, and I'll say by using the slope, and y-intercept. If we were going to use a slope and y-intercept, that means we're writing our equation in slope-intercept form, and then we're going to plot the y-intercept, that's our starting point, and then we're going to apply the slope. Okay, your slope is either rise over run or it's fall over run. We're always going to run to the right. The second method for graphing would be by plotting the x and y intercepts. Right? We've done this already. If you want to find the x-intercept, that's going to be x comma 0. So you'll figure out what x is by plugging in 0 for y. If you want the y-intercept, you can simply plug in 0 for x and then solve. And we did this in Unit 4. And we have those videos. In case you ever wanted to see that again, go ahead and recap with that video. Your third method of graphing is simply by plotting points. What I've learned from you guys is that you prefer the first method. You prefer writing the equation in slope-intercept form and then graphing by plotting the y-intercept and then applying the slope. So that's cool. I will tell you that graphing systems of equations will end up getting really nasty very, very quick. So we're going to want to potentially avoid graphing, and instead we want to use either substitution or elimination. Substitution's a nice method, but you will all end up preferring, and I know this because I've been doing this for 12 years now, you'll all prefer elimination, and I actually do as well. You'll see all 3, but I'm betting anything that you'll end up preferring elimination. Let's turn the page. Let's see this in action. Number 1, we want to solve the following systems by graphing. This is very important. In your Lumen homework, you're going to be given instructions. They'll say, solve the system by graphing, or solve the system by substitution, or solve the system by elimination. Be careful with the instructions here, okay? Because we are asked to solve the system by graphing, what we want to do is write each equation in slope-intercept form, and then we want to check it out. So we have y minus x is equal to -1. We notice here that this is not in slope-intercept form yet, but we want to write this in slope-intercept form. So what I'm going to do is I'm going to add x to both sides. That leaves me with y is equal to, and instead of writing -1 plus x, we're going to put the positive x first and the -1 second. We want to write this in descending order. So y is equal to x minus 1. Perfect. This is in slope-intercept form. We recall that slope-intercept form is y equals mx plus b. So the m is the coefficient of our x term. The m here, even though it's not written, is a 1. So my slope is 1. I want to write that as a fraction, so it's going to be written 1 over 1. My y-intercept is the b term. My b term in this case is -1, so we write the y-intercept as an ordered pair. We know that the y-intercept is 0 then the number, because how else are you going to be on the y-axis, right? -1, 0 is here. That's on the x. You want to be on the y-axis. So 0, -1 is right here. Once we plot 0, -1, I'm going to apply the slope. The slope tells us +1 over 1, which means rise 1, run 1. So rise 1, run 1. I'm going to do it again. Rise 1, run. Rise 1, run. Again, and again, and again, and again, because I want to. So I'm going to take my straight edge and I can't even talk. I'm going to connect all of these. Okay, that leaves me with this particular line. I need a better straight edge. Ooh. There you have it, my messy line. So that's the first equation graphed. We still have to do the second equation. So we have y plus x is equal to 3. Again, we want y completely on its own, so we're going to subtract x. That gives me y is equal to -x plus 3. Hi, Haley. At this point, again, our m is the coefficient in front of x. You're not just going to say the coefficient is a negative. That doesn't even make sense. You got to give me a number. So even though it's not written, it's going to be a -1. So your slope here is a -1. We're going to write it as a fraction, which means we're going to put this over a 1. Your y-intercept is your b, and the b term is 3, which means your y-intercept is 0, 3. So again, we're going to plot the point 0, 3. So 1, 2, 3. We're going to plot that point. That's our starting point. And then we're going to apply the slope. Because our slope is a -1 over 1, this means fall 1, run 1. So from this point, we're going to fall 1, run 1. Fall 1, run 1. Fall, run. Fall, run. Fall, run. And now let's connect it with a straight edge. Once we have graphed both lines on the same coordinate axis, we are going to identify the intersection, the point of intersection. Notice here is where the two lines cross each other. That particular ordered pair is 2, 1. So the solution is the ordered pair 2, 1. So I'm going to write here, I'm going to point here, and I'm going to say that's the solution. 2, 1. Remember, the solution is always going to be the point of intersection, where the two lines cross each other. Very cool. Let's look at our next problem, number 2. So notice each of these equations. We have x minus 3 is equal to 4. That's weird. And then we have 2y minus 5 is equal to 1. Well, from our original problem, from our first problem, we wanted to rewrite each equation in slope-intercept form. But if we look at this, we only have one variable, and that's okay. even if you have just one variable, shouldn't you try to solve for it? If I try to solve for x and I add 3, I'm left with x is equal to 7. But we learned that this is a specific line. If you know that x is 7, let's think about what that means. X is 7. So I'm going to go over to x, 1, 2, 3, 4, 5, 6, 7, and I'm going to plot that point. If x is 7, that ordered pair that I just plotted is 7, 0. We had a discussion last week where if we wanted to graph a line, we needed to plot 2 points. Well, where am I going to put my second point? Well, think about this. Your equation says x is 7. So if I wanted to find another point, I have to make sure that no matter what I do, x is 7. So I'm going to make x 7, and you could fill in any number you want there. I'm going to fill in 4, just because I feel like it. It literally could be any number you want. And the reason is, it only says x is 7. So that could be any ordered pair you'd like. So I'm going to call that 4. Let's plot the point 7, 4. So 7, 1, 2, 3, 4. And voila, I have my vertical line. If you recalled from Unit 4, you would say, oh yeah, that makes sense. When you have x is equal to x is equal to a number, that's a vertical line, and it'll always be a vertical line. Next, we want to solve our second equation, 2y minus 5 is equal to 1. So in this case, I only have one variable again. Not a big deal. As mathematicians, you want to solve for that unknown. You want to solve for that variable. So we're going to add 5 to both sides. That leaves me with 2y is equal to 6, and I take the next step and I divide by 2 and I get y is equal to 3. Very cool. Now, if y is 3, I want to go ahead and plot that point, or what it feels like where y is 3. So I'm going to go over to y and I'm going to plot 1, 2, 3 right here. Y is 3 at that point. So essentially, that ordered pair, oops, I apologize. That ordered pair is 0, 3. Now, same conversation as we had with our x. If we're told here that y is 3, then we need another ordered pair, but y has to be 3. X can be any number you want it to be. So in this case, I'm going to make it a 2, just because I feel like it. So 2, 3, 2, 3 is right here. Beautiful. We notice that this is going to be a horizontal line. And we've seen this in Unit 4 as well. Perfect. Once we have graphed both of these lines, we can say, oh, the point of intersection is the solution. It should be of no surprise to you that the point of intersection, or our solution, is 7, 3. That should not be a surprise. It's literally telling you that to solve this system, x is 7 and y is 3. Okay, that's the point of intersection, 7, 3. So we're going to write solution is 7, 3. Not bad. Let's turn the page. Hyder, you asked a really good question. Recall that x has to be 7, but y could be anything you want it to be. So when I made x 7 here and here, I plotted 7, 0 because when I first plot that point, it gives me a sense of, okay, I know x is 7 and I know for sure that x is 7 right here. But Hyder, you need a second point to plot the line. So what I did was I ensured that my x was 7, and you can literally pick any number you want for y. Any number you want. That could have been 7, 1, 7, 2, 7, 3, 7, 4, 7, 5. It doesn't matter. The only restriction is that x has to be 7. So x is 7. Y could be anything you want it to be. Same thing here. If y is 3, x could be anything you want it to be. The only restriction is that y has to be 3. So I came up with these 2 points. And and then I plotted it. You already know that y equals 3 is going to be a horizontal line. You also know that x equals 7 is going to be a vertical line. And this is just the knowledge we have from Unit 4. So make sure you're practicing that so that this makes sense. Let's turn the page. Okay. We are going to now talk about substitution because technically we're trying to stay away from graphing if we can to solve most of these systems of equations. We'll end up using either substitution or elimination. So I'm going to walk you through the idea of substitution. According to substitution method, the step number 1 is you want to isolate one of the variables. That is completely up to you. Now, if you're going to isolate one of the variables, you want to use strategy. Okay? You want to use strategy when you isolate one of the variables. So here's what I mean by that. Take a look at this system. I have negative 4x plus y is equal to 6, and I have negative 5x minus y is equal to 21. Well, if I wanted to isolate one of the variables, I get to choose which equation. It doesn't even matter. I get to choose which variable and which equation. But again, I want to use strategy when I do this. So if I look at this first equation, negative 4x plus y is equal to 6, do you agree that getting y by itself would be really, really easy? If I wanted y completely on its own, all I have to do is add the 4x to both sides. That cancels the negative 4x and it brings a positive 4x over here. Awesome. In one step, I get y by itself. Let's say I'm looking at this second equation. Let's say I'm looking at both of these terms and I say, I think I want to get y by itself here. Let me show you what that would look like. If I took negative 5x minus y is equal to 21, and I said I want y by itself here, I would add the 5x. I get negative y is equal to 5x plus 21. And then, to get y completely on its own, I would divide by negative 1. Which means my equation is y is equal to negative 5x minus 21. That wasn't bad either. That wasn't terrible. When we think about using strategy, what we want to try to avoid is having a ton of fractions to work with. When we want to isolate one of the variables, I would recommend trying to isolate a variable with a coefficient of 1 or something that makes it a little bit easier to work with. Technically, you could solve for any variable you want. But I'm telling you, if you can avoid all of those fractions, you should. Just save yourself some of the hassle. Okay, so take a look at what I did here. I wanted to get y by itself in my first equation, so I brought the 4x over, and then I have y is 4x plus 6. Do you see how this is bolded? I don't know if you could tell that. But y is 4x plus 6. So I'm going to put a circle around 4x plus 6. What I have just done is I have just manipulated the first equation. And I said, according to the first equation, y is 4x plus 6. Now, guys, this is a system of equations. So if you manipulate one of them, you want to plug that into the other equation. So take a look at what I wrote here. Plug this expression, 4x plus 6 for y, into the other equation, the one you did not manipulate. The other equation is negative 5x minus y is 21. So if my other equation is negative 5x minus y equals 21, well, I know what y is. Y is 4x plus 6. So I'm going to take 4x plus 6 and put it right into y in my second equation. Notice how I make this substitution. If I say that y is 4x plus 6, I better use parentheses. I better use parentheses to show that I'm making that substitution, and everything else stays the same. Negative 5x minus, but instead of y, I have 4x plus 6, and then equals 21. At this point, I'm going to solve. So I'm just going to rewrite the problem here so that you can see each of the steps. Sometimes it's helpful to do that. And why not? If I'm going to solve, I need to distribute to drop parentheses. That gives me negative 5x, negative 4x, negative 6 is equal to 21. Now I'm going to combine like terms. A negative 5x and a negative 4x is a negative 9x. I bring everything else down. Next, I'm going to add 6 to both sides. That gives me negative 9x is equal to 27. And then I'm going to divide by negative 9. That gives me x is negative 3. Very cool. Notice when we started this particular system of equations, we had two unknowns. We had an x and we had a y. You should want to find both of them. You should be curious about both of those values. If you find one of them, you gotta find the other. So here's how we do it. Once you find one of your values, so we found that x is negative 3, you're going to take this value and plug it into either of the equations. So I want to show you what I did. I know that x is negative 3, so I rewrote the first equation. After I rewrote the first equation, I replaced x with a negative 3. And then, guys, I did the math. So I have negative 4 times negative 3 plus y is equal to 6. When you multiply these, it gives you a positive 12. So 12 plus y is equal to 6. I brought the 12 over and I get y as negative 6. Now, what I want to prove to you is that I could have taken this value and plugged it into either one and I will get the same result. Let's look at that. So I'm going to rewrite the second equation instead. X is negative 3. So I'm going to make x negative 3 in my equation. Notice how I made the substitution, and when I made the substitution, I used parentheses. That's very important. Please do the same thing. Negative 5 times a negative 3 is a positive 15. I'm going to subtract 15 from both sides. I get negative y is equal to positive 6. And then I'm going to divide both sides by negative 1. And we found that y is negative 6. Do you see how I ended up with the exact same answer, regardless of which equation I plugged the negative 3 into? The reason this works is because this is a consistent system. That means that I have two lines that intersect at the same point, right? It's like two lines crossing. They'll intersect at the same point. So my answer would be the ordered pair, negative 3, comma, negative 6. Make sure you have parentheses around that. All right, now that we've gone through this step by step, and notice your instructions are here. So as you try this at home, take this sheet out, keep it next to you. Go through each of these steps as you move through the problem in your homework. Don't be afraid to do that, or rewatch the video, no big deal. Let's try another one together. So we have 3x and minus 2y equals 5, and we have x plus 10y is equal to 7. Okay, cool. If I wanted to get x alone here, I'd have to add the 2y, and then I'd have to divide by 3. Ugh, I don't want to do that. If I want negative 2y, or if I want y by itself, I'd have to subtract the 3x, and then I'd have to divide everything by negative 2. Nah, I'm good on that. If I wanted x alone, all I have to do is subtract 10y. Ding, ding, ding. That's exactly what we want to use. We want to use strategy to find the easiest variable to isolate. So in this case, I'm going to take the second equation, x plus 10y is equal to 7, and I'm going to isolate x. In this case, if we isolate x, all we have to do is subtract the 10y. And now I have x is equal to negative 10y plus 7. This is awesome. By isolating x in my second equation, I didn't have to worry about a whole bunch of fractions. It's nice, neat integers, and I could work with that all day long. Once you isolate x in the second equation, we are going to take this expression and plug it into the first equation. So I have 3x minus 2y is equal to 5. But I know what x is. X is negative 10y plus 7. X is this entire expression. So I'm going to take this entire expression and plug it in for x. Rewriting this, I get 3 times, make sure you have parentheses there, negative 10y plus 7 minus 2y is equal to 5. Do you see how only x was replaced with a negative 10y plus 7? But every other part in the equation remained exactly the same? Good. That's what you're looking for. You simply want to make a substitution. Now we're going to solve. Remember, you must distribute to drop parentheses. So that gives us negative 30y plus 21 minus 2y is equal to 5. Let's solve. Negative 30y and another negative 2y, well, that's going to give us negative 32y. They have the same sign, so you sum them and keep the sign. If you're in the whole 30 bucks and you lose another $2, oh, you're in the whole 32. We are going to subtract 21 from both sides. That gives me negative 32y is equal to negative 16. And then I'm going to divide both sides by negative 32. Notice that the negative and a negative will cancel, so my answer is definitely going to be positive. But I'm not going to leave my answer 16 over 32 because I can actually reduce this. I can divide both of these numbers by a 16. So 16 divided by 16 is 1. 32 divided by 16 is 2. So my y value is 1/2. Very nice. I found my value for y, but I still need to find my value for x. So you can take this value and you could plug it into one of the originals, or you could take this value and plug it into the equation you manipulated. It really is up to you. The safer approach would be plugging it into one of the originals in case something went wrong here. And what you may want to do is plug this into both of them to make sure that you get the same answer. So because I have so much room here, I'm actually going to plug it into both of them. So I'm going to write both equations. We have 3x minus 2y is equal to 5, and I'm going to write x plus 10y is equal to 7. So I know that y is 1/2. So we're going to take this, and I'm going to replace the y here, and I'm also going to replace, and I'm going to replace that y as well. Okay, we're going to do both of those, and just to see what happens. So we have 3x minus 2 times 1/2 is equal to 5. Well, if you have 3x minus 2 times 1/2 is equal to 5, well, that's easy. What's 1/2 of negative 2? 1/2 of negative 2 is a negative 1. So 3x minus 1 is equal to 5. Add the 1. 3x is equal to 6, and then we divide by 3. X is equal to 2. Let's take a look in the second equation and see if we get the same answer. We have x plus 10 times 1/2 is equal to 7. 1/2 of 10 is 5. So x plus 5 is equal to 7, and now we subtract 5. What do you know? X is equal to 2. So that means the solution to your system is 2, 1/2. And we're done. You do not have to plug into both equations, but if you do, it's a check, isn't it? If you plug your answer into both original equations and you get the same result, you've just checked it, which means you know that you solved this successfully. Another way to check your answer would be to plug in your answers into your equations. So for instance, you're saying that x is 2 and y is 1/2. So if I plug it into here and here, I better get 5. So 3 times 2 is 6, minus 2 times 1/2 is 1, so 6 minus 1 is 5. Yep, that worked. We can do the same thing with the 2.5 in the second equation. So x is 2, y is a half. So 2 plus 10 times a half, or 2 plus 5 is 7. Yep, that worked as well. Alyssa, you asked a great question. You could also write your answer as 2 comma 0.5. That would be totally cool in this case as well. Because remember, we are graphing these, right? And actually, more often than not, I won't ask you to graph them. I'll ask you to use substitution or elimination. But these are lines. So if you had to graph them, we could graph in this way, the point 2.5, the ordered pair. Okay? Excellent question, Alyssa. All right. Take a look at number 2. We have 2x plus 3y is equal to 9. But then, notice the second equation. Y is negative 3x minus 4. I want you to think about this and say, holy crap, I was just given a gift. If I'm telling you that y is negative 3x minus 4, then we already know that we can take that expression and plug it into the other equation. Looking at the second equation, y is negative 3x minus 4, we are going to take 2x plus 3y equals 9, and we're going to make a substitution in place of y. So I'm going to take this expression and plug it right in there to replace y. Again, remember this is a system of equations. So those two equations must work together. You don't want to take this and plug it into itself. That doesn't make sense, right? You always want to manipulate one equation and plug it into the other one. Cool. So we are going to rewrite the equation, except we know what y is. Y represents negative 3x minus 4. So we're going to put that right here. And we're going to distribute and solve. The really cool thing about this part is that when we're getting into solving this linear equation, we're right back into unit 2. So we're right back into stuff we did like our first month of classes. Let's distribute. That gives us 2x minus 9x minus 12 is equal to 9. 2x minus 9x is negative 7x. Minus 12 is equal to 9. I'm going to add 12 to both sides. And that gives me negative 7x is equal to 21. And what do you know? We get a nice, neat number. We get that x is a negative 3. As a reminder, if you wanted to, since we know that x is negative 3, I can plug it into both of the original equations and make sure I get the same y value. So I'll do that just to show you what it looks like again. So we have 2x plus 3y is equal to 9. And our second equation is y is equal to negative 3x minus 4. Well, I know that x is negative 3. So I'm going to do it again, and I'm going to replace x with negative 3, and I'm going to replace x with negative 3. You like my dotted lines? I hope so. So replace x with negative 3 for both of these, and let's solve it. Do you notice that no matter what, when I made the substitution, I put the negative 3 in parentheses? That's exactly what you're looking for. You want to make sure you use parentheses when you make a substitution. So that leaves me with a negative 6 plus 3y is equal to 9. And I'm going to solve this guy. So let's add 6. 3y is equal to 15. Divide by 3. Y is equal to 5. No big deal. We're going to do the same thing for the next problem and see if we get the same answer. Y is equal to negative 3 times negative 3 is a positive 9. Bring down the minus 4. And what do you know? Same thing. We did it right. So the solution to my system is negative 3, 5. Remember, you want it to be x, then y, because this is an ordered pair. It's a point on the graph. So be super careful. when you do this. Okay? Very nice. As always, if you have any questions, don't hesitate to ask in the live chat. But let's keep going. This is looking awesome. Okay. Next, we have 2x plus 3y equals 6 and 4x plus 6y is equal to 12. Again, we can choose any variable to get by itself. We could get the 2x by itself. We could get the 3y by itself, the 4x, or the 6y. It doesn't matter. It's totally up to you. Unfortunately, in this case, we're going to end up with a fraction or two, and that's not a big deal. I don't want you to panic and think that you can't work with a problem that has a fraction, because that's absurd. So I'm just going to choose a variable at random. Let's do this one. So I'm going to get 3y by itself. So let's manipulate 2x plus 3y is equal to 6, and I'm just going to isolate my y term. In order to isolate my y term, I'm going to subtract 2x. That leaves me with 3y is equal to, and this is not just 6 minus 2x. We want to write this in descending order. Negative 2x plus 6. Next, I want to isolate, excuse me, I want to isolate y by dividing by 3. That gives us y is equal to negative 2/3 x plus 2. That's not that terrible. It's not that gross. Notice here, guys, how I manipulated the first equation, right? This whole time I manipulated the first equation, and I found that y is negative 2/3 x plus 2. What I can do now is take this expression and plug it into y for my second equation. So I'm going to rewrite 4x plus 6y is equal to 12, and I'm going to replace y with this expression. That gives us 4x plus 6 times negative 2/3 x plus 2 is equal to 12. Let's distribute and solve. We get 4x, 6 times negative 2/3. Remember, that's like 6 over 1. I'll do some side work for you guys. And I'll write this as side work. Even though at this point, you guys should be masters at multiplying, dividing, adding, subtracting fractions. You should be masters at this. So 6 times negative 2 over 3. That 6 we can write as a fraction. It will be written over 1. When we multiply fractions, we're allowed to reduce. Notice we have a 6 here and a 3 here. We can divide out a 3 from both the numerator and denominator. So divide out a 3 leaves us with a 2 here and a 1 here. When I multiply straight across, I get 2 times negative 2, which is negative 4, and 1 times 1, which is 1. So this is simply minus 4x. Then I have 6 times a positive 2. So that's 12. Notice what just happened. You have 4x minus 4x. Well, that wipes each other out. These are opposites. They completely wipe each other out. So if these two wipe each other out, they cancel each other, and you're left with 12 is equal to 12. The really cool thing about this, guys, is that that's a true statement. So because this is a true statement that we're looking at, we know that 12 is equal to 12 would represent infinite number of solutions. We learned when we first started this packet that the only way that's possible is if these two lines are the exact same equation. And they actually are. So as a note here, this is a dependent system. Okay, that's a dependent system. You're probably thinking, well, how did I know that? Hyder, you asked, does it always have to be substituted into the second equation? Whichever one you manipulate, you must plug into the other equation. Otherwise, it's not a system. The two equations have to work together. So if you manipulate one, you always have to plug it into the other. Always, always, always. Now I want you to notice these two equations. We have 2x plus 3y equals 6 and 4x plus 6y equals 12. Do you notice anything interesting? What would happen if I multiplied every term here by 2? I'm allowed to do that, right? When I solve equations, when we learned in Unit 2 how to solve equations, we learned that if we multiply or divide, we have to multiply or divide every single term in an equation by the same value. In this case, what if I said I wanted to multiply everything here by 2? If I multiplied every term by 2, I end up with 4x, 6y, and a 12. They're the same equation. The interesting thing about this is that if you notice right away that they're the same equation, you could simply write infinite number of solutions. So we did a lot of math to prove exactly that, but if you had identified that from the very beginning, you're like, wait a second, these are the same equation, then you're golden. You can say infinite number of solutions. Let's take a look at number 4. Okay, this time I want you to do number 4. I want you to find a variable to isolate, and it could be any one that you like. You could get 3x by itself, you could get y by itself, you could get 6x by itself, you could get 2y by itself, whichever term you want to get alone. And then substitute that into the second one, and let me know what you guys get. So I'm going to give you 2 minutes to play around with this. In the live chat, please let me know what you got for your answer. Okay. So I'm seeing some answers in the live chat, and that's fantastic. We had an answer within like seconds. So notice here that we could do this in a couple ways. We can recognize that isn't 6 double 3 and isn't 2 double 1, but 9 is not double 8. So that's kind of a hint towards the solution, but I want to show you what we would do. So if I were you, I would take the first equation, 3x plus y is equal to 8, and I would get y by itself. That would be the easiest term to isolate. So we're going to subtract 3x from both sides, and that gives me y is negative 3x plus 8. Next, I'm going to take my second equation, 6x plus 2y is equal to 9, and I'm going to take this expression, and I'm going to plug it in for y, right in there. So I get 6x plus 2 times negative 3x plus 8 is equal to 9. Now I'm going to solve it. We know how to solve this. We know that we have to distribute. So we get 6x minus 6x plus 16 is equal to 9, right? Because we distributed. 6x minus 6x, those go away. They completely cancel. So you're left with this statement. That is utter chaos. There's no way that you can tell me that 16 is equal to 9. I'm going to be like, nah, I don't think so. And if you believe that 16 is equal to 9, I'm going to say, let me borrow 16 bucks, but I'm only going to give you 9 back because they're the same, right? That's a problem. So because of this absurd statement, you can write that the answer is no solution. Okay? The only situation, the only scenario where you would graph lines and there would be no solution would be if the two lines are parallel. Okay? We know that they are parallel because they do not intersect, so there's no solution, which means that this system is actually inconsistent. This is an inconsistent system right here. The lines are parallel, so they have the same slope, which means they'll never cross. Not bad, right? Good. Let's keep going. We're doing awesome. I'm loving this. We are ready for my favorite, and that is elimination. All right. With elimination, all you want to do, now I'm going to go back to me. With elimination is super nice. Okay, it's like one of my favorite methods for solving systems of equations. what you have to consider when you're using elimination is you have to consider how to make terms opposites, right? So for instance, the opposite of a positive 4x is a negative 4x. And that's because when you take the 4x and you add negative 4x to it, they wipe each other out, leaving you with 0. Okay, 0, nothing, nada, right? Okay. The opposite of a negative 10y is a positive 10y. They wipe each other out, they leave you with nothing. But sometimes it's not as straightforward as that. Sometimes you have different terms, like let's say you had a 2x and a 5x. Well, those aren't going to wipe each other out. But you can turn them into something that will wipe each other out. So again, let's say you had a 2x and a 5x, right? So in order to make them wipe each other out, shouldn't you find a common multiple? So a common multiple of 2 and 5 is 10. So what you'll want to do is to make those terms a positive 10x and a negative 10x. And that's how they'll wipe each other out. Now, in order to do that, you'll end up having to multiply each equation by a different number, and that's not a big deal. And you'll see that it's not a big deal. You find a common multiple, and then you simply multiply one or both of the equations by a number to make sure that they wipe each other out. That is the goal. You want to eliminate those terms, okay? You choose either x or y, or whatever the variable is. You choose to eliminate one of the variables, and then you figure out what you have to multiply by, if anything, to make sure that they cancel. All right? Now, I'm actually going to skip the rules because you can read that on your own. What I want to do is I want to jump into a problem because I feel like we're in a really good place right now and we have that momentum. So let's look at a problem together. I'm going to skip this page and let's look at an example. All right. So the first thing I'm going to do is I'm actually going to rewrite the system. I always rewrite the system. So we have 3x plus 5y is equal to negative 6. And I have negative 2x plus 7y is equal to 4. I love it. Now, I want to assess what's happening here. So we have a 3x and a negative 2x. Well, those aren't going to cancel each other out right now because they're not opposites. We have a 5y and a 7y. Those are definitely not going to cancel each other out because they're not opposites. Not a big deal. In this case, I'm actually going to look at my x terms, a 3x and a negative 2x. I already have an inclination towards these two because one's positive, one's negative. So half the battle is already done. So then I have to say to myself, well, what's a common multiple of 3 and 2? And you're going to say, well, a common multiple of 3 and 2 is 6, right? The multiples of 3 are 3, 6, 9, 12, 15. The multiples of 2 are 2, 4, 6, 8, 10, etc. So notice they both have a common multiple of 6. Recall that if we want to use elimination, we want to make opposites. Let's try spelling correctly. We want to make opposites, right? We want to make additive inverses of each other. So if I want my 3x to become a 6x, well, that's easy. All I have to do is multiply the entire equation by 2. If I want my negative 2x to become a negative 6x, well, that's easy. All I have to do is multiply this guy by 3. Now, let me show you what happens. What I'm going to do in this case is I have to distribute the 2 throughout the entire equation. Notice my lines of distribution, even though they're all scraggly and weird. You have to distribute the 2 to every term in the equation. You don't get to pick and choose. Remember the rule. So 2 times 3x is 6x. 2 times positive 5y is positive 10y equals 2 times negative 6 is negative 12. Cool. I'm going to do the same thing for the second equation. 3 times a negative 2x is negative 6x. Ooh, yeah, that's what I wanted. 3 times 7y is a positive 21y. And 3 times 4 is positive 12. Cool. I love it. We wanted to make our x terms opposites, and they are. A 6x minus 6x, well, they cancel each other out. It's completely gone. You are not left with an x. Please be careful with that. If you have 6x and you take away 6x, you've got nothing. You've got 0, and that's okay. Next, we have a positive 10y and a positive 21y. Well, that's easy. That gives me a 31y. Because they're both positives, we're definitely going to add them, right? And then I have a negative 12 plus 12. When you don't see a sign here, that's a plus, right? You have to have a negative sign to indicate negative or minus. So a negative 12 plus 12, well, those cancel also, but it leaves you with a 0. Next, I'm going to isolate y by dividing by 31, and I find that y is 0. Okay, cool. Again, no big deal. Once I have one of my variables, you need to plug into one of the originals to find the other variable. Notice our system of equations has x and y. If I find y, I better find x. If I find x, I better find y. So I'm going to take this answer and plug it into one of the originals. I'm not going to plug it into both because we've already seen that. So I'm going to take 3x plus 5y is equal to negative 6. And I know that y is 0, so I'm going to plug that in right here. So we have 3x plus 5 times 0 is equal to negative 6. Notice how this is the same process as substitution. Once you found one of the answers, you plugged it into an original. Same thing. Same thing we did in substitution, we do in elimination. It's the first part that's different between the two methods. Hopefully you like this first part. I do. I think it's cool. So we have 3x is equal to negative 6. I don't have to write plus 0 because 3x plus 0 is 3x. So I'm just going to leave that out. Divide both sides by 3. And we have that x is negative 2. Which means our solution is the ordered pair, negative 2, 0. And that's it, guys. That's all we have to do for elimination. Let's do it again. For our second problem, we have 4x plus 5y is equal to 3. And we have 2x minus 3y is equal to 1. Okay, let's have this conversation again. If I look at my x terms, I have a 4x and a 2x. Well, the cool thing about this is that a common multiple of 4 and 2 is 8, but even smaller is 4. Isn't 4 a common multiple of 4 and 2? Yeah, it totally is. So if you have a positive 4x, then the other's got to be a negative 4x. But let's hold off on that for a moment. I want to look at the y terms. I want to look at my 5y and my negative 3y. So notice here I have a 5y and a negative 3y, and we have to think, well, okay, they're already opposite signs. One's a positive, one's a negative. So that's half the battle already done. But I have a 5y and a 3y, and okay, well, a common multiple is 15. So if I wanted to make these opposites, I would have to multiply the top equation by 3, because 3 times 5y is a positive 15y. And I'd have to multiply the second equation by 5, because 5 times a negative 3y is a negative 15y. So that will work. The cool thing about elimination is that you get to choose whichever variable you want to eliminate. Now, after having this conversation about which variable to eliminate and how you would do that, I'm actually just going to eliminate x because I want to. It's my personal preference. You don't have to. So I want to eliminate x here. If this is a positive 4x, I can easily make this into a negative 4x by multiplying this entire second equation by negative 2. This is pretty cool because I actually don't have to multiply the top equation by anything. I could leave it as is. I can leave it untouched. So I'm going to rewrite the problem. 4x plus 5y is equal to 3. And then I'm going to distribute the negative 2 through the second equation. Please draw the lines of distribution. If you draw the lines of distribution, you won't forget to distribute the negative 2 throughout the entire equation. I've seen so many students forget to take this negative 2 and multiply it by the 1. They'll forget to do that and they leave it a 1. And that's a problem. You'll get your answer wrong every single time. So be super careful. That gives us a negative 4x. Negative 2 times a negative 3y is positive 6y. And then negative 2 times a positive 1 is a negative 2. Awesome. Notice here my 4x and negative 4x, they cancel. That's gone. And I have 11y, right? 5y and 6y is 11y. 3 minus 2 is 1. And I divide by 11, and I find that y is 1 over 11. Okay, that's fine, right? We have y as 1 over 11. That's totally fine. You're probably thinking to yourself, I really don't want to substitute 1 over 11 into either equation. I don't want to do it. I mean, you should practice doing that anyways because, I mean, it's the math behind it. But I want to show you an alternative that you just might like. What if, instead of substituting 1 over 11 in place of y and then solving, what if instead I started the problem again? What if I rewrite the problem? 4x plus 5y equals 3 and 2x minus 3y is equal to 1. And what if this time I eliminated y? If I eliminate y instead, I'll get x. And I can get x without ever having to plug in 1 over 11 into one of the equations. I'll show you. So if I want to eliminate y's, I want them to be 15s, right? So that means I'm going to multiply the top equation by 3 and the second equation by 5. The really great thing is they're already opposite signs, so I don't have to worry about multiplying by a negative. You just leave them as is. Let's distribute. Draw your lines of distribution. So 3 times 4x, 12x. 3 times 5y, 15y. 3 times 3, 9. 5 times 2x, 10x. 5 times a negative 3y, negative 15y. Ooh, that's exactly what we wanted. Is equal to 5 times 1, which is 5. Awesome. These are both positives. So, duh, we're going to add, right? They're both positive. 12x plus 10x is 22x. Those are gone. These are both positives. 9 plus 5 is 14. Divide by 22. And you get that x is equal to, and you're never going to leave it like this. I know for a fact that all of you that are seeing this fraction are saying to yourselves, wait a second, I can reduce that. In order to reduce this, I'm going to divide both the numerator and the denominator by 2. 14 divided by 2 is 7. 22 divided by 2 is 11. So my solution is 7 over 11, comma, 1 over 11. That's your answer. Now, before we do another problem, and we actually won't have time to do another problem today, I want to show you really quickly what it looks like if you were to plug in 1 over 11. So this is just kind of for your reference. You can write it down if you want. You can do whatever your heart desires. I'm going to take that y equals 1 over 11, and I'm going to plug it into one of the originals. It doesn't matter which one. So I'm going to take the second equation, 2x minus 3 times 1 over 11 is equal to 1. I'm going to show you a technique that we learned in Unit 2 that is still present today. It never goes away. Math builds, right? You don't just like use pieces and throw them away. No, no, no. Math builds on itself. So everything is useful as you go along. So 2x minus 3 times 1 over 11 is 3 over 11. Remember, that's over 1, so 3 over 11. And that's equal to 1. We learned in Unit 2 that whenever we have fractions in our equation, we're allowed to multiply every single term by the LCD. My LCD in this case is 11. If I multiply every term by 11, notice what happens. I get 22x minus, notice the 11's cancel. That was the point. When we multiplied by the LCD, we're able to eliminate fractions. So it becomes minus 3 is equal to, and then 1 times 11 is 11. At this point, I'm going to add 3 to both sides. That leaves me with 22x is equal to 14. And are you seeing it already? How cool is that? Divide both sides by 22. And voila, you have the x is 7 over 11. I hope that it was helpful to you guys to see both methods of saying, you know what, I don't really want to plug in that fraction, so I'm just going to eliminate the other variable instead. That works. That'll work every time. But if you wanted to plug in that fraction, that's what it could look like. This is an approach you could take for solving for the other unknown. So you have options here. As always, you have options. All right? Have a great break, guys. See you in 2 Tuesdays. Bye.